Section 5.2, Practice A, we're going to find the length of segment CD. And segment CD is a different part of each of these diagrams. So in this diagram, they mark segment CD congruent to segment DA. So whatever segment CD is, you know it's got to be the same as segment DA. So a real simple way to do this is to just write these expressions, and since they're the same, you make them equal. Subtract 2x from both sides. Divide by 2. Find the length of segment CD is what they ask you to do. Segment CD is this guy. X is just part of that. It's 2 times 2 plus 4. So this length, C to D, is 8. That's your answer. You just plug back in. Now, this did not use anything about perpendicular bisectors. You have an isosceles triangle. Those parts are the same. Well, actually, we do have a perpendicular bisector here. Now, same concept here. This didn't use the perpendicular bisector theorem, but this one will. This is definitely a perpendicular bisector. It's coming down, it's touching this segment at a right angle, and B is definitely the midpoint. This is the perpendicular bisector of this. So the theorem tells you that if a certain point is on a perpendicular bisector, like point D is on the perpendicular bisector, then it is equidistant from the endpoints of that segment. So the endpoints of the segment are A and C. So that means from D to A is the same as the distance from D to C. So you're basically setting those expressions equal, and you're solving for x. X is 1. Remember, they want you to find the distance from C to D. 3 times 1 is 3, plus 1 is 4. Now, the rest of these are the same. This is a perpendicular bisector. Point D is on the perpendicular bisector, so you know these are the same. Likewise, this is a perpendicular bisector because these are the same. So you know that this distance is the same as this distance. That's the perpendicular bisector theorem. In this diagram, the perpendicular bisectors of triangle MNP, that's the big one, meet at point O. So what kind of point is point O? Remember, that's called a circumcenter. That's where all of your perpendicular bisectors come together. So these dashed segments here, those are your perpendicular bisectors. And are shown dashed. Well, there we go. Find the indicated measures. So it helps you to make these marks here. Find the distance from M to O. M to O. All right, so O is that circumcenter. How far is it from M to the circumcenter? Well, remember, N to the circumcenter, they tell you here, it's 26.8. Those distances are the same. That's the important part about the concurrency of your perpendicular bisectors. That point is a special point. It's the same distance from each vertex. So it's 26.8. Number 6, find the distance from P to R. Here's P, here's R. What's the same as this one? Number 7, M to N. This guy's 20, this guy's 20, so the whole thing is 40. S to P, 44. No, not 44. M to P is 44. Whoops. S to P is 22. Sorry about that. Number 9, Q to N, 20. Tell whether the information in the diagram allows you to conclude that C is on the perpendicular bisector of segment AB, and then explain. Well, this is a perpendicular bisector. We've got the right angle. E is definitely a midpoint because those are the same. Is C on the perpendicular bisector? We can't really tell because that maybe it goes through it, maybe it doesn't. But the converse of the perpendicular bisector theorem tells you, even though if you don't know if that point's on the perpendicular bisector, you can figure it out if this point is equidistant from those endpoints, and see how it's marked the same? So this will go through that point C. So yes. What was the reason? It's the converse of the perpendicular bisector theorem. I don't remember what number that was. Might have been like 5.3 or something. How about this one? Is point C on the perpendicular bisector of segment AB? Well, there's not even a perpendicular bisector there, but would it be if it's equidistant from it? So if I would draw a segment down here that's perpendicular and touches that midpoint, that's the perpendicular bisector. Point C would be on it. So you could use that converse of the perpendicular bisector theorem again if you like, or you could even argue that's an isosceles triangle. And we know things about isosceles triangle. We know that's a perpendicular bisector. We know it splits the triangle into two congruent triangles.